Okay, so for today, I'm going to, for those people who will be watching the video later on, the first thing we talked about is that you can use any text editor uh, for these ones. Even a notepad would suffice if you really don't care about highlighting the code or anything like that. But if you use any decent code editor that highlights the codes would be much easier to edit the codes. But what we will be doing for the remainder of this course is that we will be just using a simple text editor, um, no IDE or anything is required for these purposes. Of course, if you have an IDE and you want to use it, you're welcome to do so. Uh, but I personally haven't used an IDE for my development purposes at all. Um, One other thing that you would need to have on your machine would be to have at least a um, modern browser, which could be, I use Google Chrome. You can use Firefox or I know Opera works. A lot of the modern browsers, Microsoft Edge now supports WebGL 2 as well. Internet Explorer and Safari still do not support WebGL 2 out of the box. Apple Safari has started to support WebGL 2 as an experimental feature, but I haven't gone around it to make the library work with that. And I don't have any interest on resolving the issues for Apple Safari because it has a very marginal share of the browser market. Right now, Google Chrome is dominating, and I think the next one that is going to overtake is Microsoft Edge, which uses an underlying Chromium browser. Uh, but if any of you later on is interested in removing the bugs, not bugs, but the supporting features so that it will start working with Safari or other browsers, you're welcome to delve into the heart of the code. um, what you will need, a little background would help, is if you know a little bit about coding. If you know HTML and JavaScript, it would help a lot. Um, I've shared a website that I used to learn for coding. It's called W3 Schools. Let me see, I can do. So if you are familiar with just these sections, if you do this background of trying to write a basic HTML page, this is basically the most that we will require from the HTML side, and just having a canvas element. The other stuff that we might probably use are IDs or things like that. So if you read about HTML IDs, you should be fine. And then the library extensively works is based on the JavaScript object-oriented programming. So most of the things that we will work with are JavaScript objects. And I learned JavaScript from this website itself. So you can um, help yourself here to learn JavaScript if you need it. Um, most of these stuff are pretty simple to follow without even going through here. But if you need a reference point for the commands in JavaScript, probably this website can also serve as a good reference for JavaScript. There are plenty of resources online for HTML and JavaScript as tutorials, so feel free to use those, but they are not absolutely necessary for here. What I'm going to be talking about today, one more time, sorry for sharing and stopping the sharing part, is these small parts, is that I will explain a little bit about the graphics pipeline, just so that you have an overview of what's happening. Probably after today, we will never come back to this part because pretty soon we will abandon most of these parts and we will start working and concentrating on the parallel programming part. And we want to be able to draw basic shapes today and understand what the vertex shaders are and the fragment shaders and what are the default geometries and vertex shaders in the library Abubu.js. Okay, so to start sharing the screen, can I share a particular application? Okay. Can you see this part, this application right now that I'm going to use for writing?
Yeah.
Okay, so the basic part that we are going to go through is we're going to talk a little bit about the pipeline. So WebGL is basically developed to draw 2D and 3D animations or geometries on the screen or the canvas element in an HTML page. And it deals with inherently 3D geometries, but the 3D geometries need to be somehow mapped into a 2D canvas so that they can be displayed. The basic geometrical primitives that we usually deal with. So we start with the geometric primitives are, the first thing is that to generate geometries, you will need points or vertices. And by connecting points, you would be able to make what?
Where's
The next lines, right? So by having points and connecting 2 points together, you will have lines. And from lines, you can make shapes, but the basic shape that you will have in computer graphics is triangles. So the idea is that any sort of surface can be meshed with a number of triangles, so that later on you can display them on the screen. So you would be able to handle basically any geometry from these three primitives. First, you need to have vertices, then you need to construct lines out of them, and then out of those you need to construct the triangles. So if you want to draw something, usually you're in a 3D space that you have X, Y, and Z, and you can have an arbitrary shape in the 3D space, that you want to draw. And the 3D space can be infinite. So you need to choose part of this 3D space that you would focus your attention into that part and only draw those parts and ignore whatever else is happening. So, for example, the camera that is showing me today is looking at the entire world, and is choosing just this opening here and what is behind the camera here. So anything that is on the other side of the camera is ignored. Anything that is out of the viewpoint of this camera is ignored. So in the graphics world, what handles this part is something called the clip space. So you choose part of this physical world, and you say that I'm going to handle these ones, only this area that is shown here. The minimum z that you will have, minimum x and y's that you have, is -1 and -1 in that corner, and the maximums that you will be dealing is this top right corner that is called that is 1 and 1 and 1. So anything out of this range would be ignored. So this is the clip space, and so usually if you have basically a general world outside that you want to render and you want to show on the screen, if you have the physical world outside, that you have different shapes and primitives there, but let's say you have this triangle in the physical world that you want to display on the screen, you have to somehow map this triangle into this clip space so that it can be displayed on the screen. So part of the graphics pipeline is basically in charge of getting the coordinates of these vertices and bringing them into this space. So let's say this coordinate here is mapped to this point, the next one is mapped to probably that point in the clip space, and this one is probably mapped to this point in the clip space. The moment these vertices are mapped into the clip space, constructing the geometries are just easy because you can immediately connect these vertices to each other with the straight lines, and those ones will produce for you produce the lines for you by connecting the vertices, and as soon as you have the lines, the triangles are formed. So the part of the graphics pipeline, in a very very basic viewpoint, the part of the program that is in charge of this process of taking the physical coordinate and mapping them into the clip space so that they can be rendered is delegated to something, part of the program that is called a vertex shader. So the vertex shader takes the physical coordinates of your points and maps them to this clip space so that you can show them on the screen later on. Now, when you have your triangles formed into the clip space, then you can start coloring this surface of this triangle. And in order to color that triangle, you break it into the smaller sections, small sections that you color them. And these ones are called fragments, and the part of the program that is in charge of coloring these fragments, of saying what is the color of each of these pixels, is handled by something called a fragment shader. So the fragment shader, after we form our geometry, we pass our vertices through our vertex shader, and we know where the geometries are in the graphics pipeline by passing the fragments through the program called fragment shader. The geometry can be colored. Now, the way that this geometry is mapped on the screen in the end is something that is handled by the WebGL engine and is handled automatically, is that this, you can consider this front part the screen or the canvas that you draw on, and everything is just mapped orthographically into this part. So basically, whatever you look at inside that, it will be colored on the screen like so. So anything behind that, if you had a geometry that is behind that, when it's going to be mapped, it would be clipped by the geometries that are in front of it, and it will be ignored. And the graphics pipeline is in charge of doing that. But those are usually for those things that you need to worry about them are in computer graphics. When you have a lot of geometries that you want to show, here we are not too much interested in mapping complex geometries into the screen and doing all those fancy stuff there. What we are interested in is how we can use this graphics pipeline to do parallel processing. So I will not go into the details of how the clipping works, how the objects are called, so-called, by the objects that are in front of them, what you can do to deal with these stuff. Those are mostly for people who are interested in just computer graphics. So in order to work with the library, we would require, we would start with a very basic program. The first example that we want to solve is a very, very simple program. We have our x and y coordinates, and z is in that direction, but we are in the x and y plane. We want to draw this simple triangle that this coordinate is 0.5 and 0.5. This is 0 and 0.5 and 0 and 0, and these have a z coordinate as well, and this coordinate here for this vertex is just 0 and 0.5 and 0. So to generate the program that is going to draw this simple geometry that we have here, we are going to getting this screen. I have posted a zip file to Canvas. If you can download that one, and if you extract it, there is a program called Hello Triangle in the best Arch. So if you extract the zip file, it will create a folder 2020 August 19. And then there is a file called 01 Hello Triangle. And there are a bunch of cheat sheets here for the next programs that I'm going to work with. So if you open it, everybody can see the editor. Is the fonts large enough?
Probably a little bit bigger, just a little bit. But we have it in our computer, that's fine.
Okay. So for the sake of the video, so that we can
yeah, that's good.
We can record it. The HTML page is very small on its own, the HTML part. It has a header part that is including the library. So to use the library and use all of the features that are available in it, all you have to do is include this single line, and that would include the library in your program so that you can start using it. And then in the HTML page, you need to have a canvas element so that you can draw on it. So this is the canvas element with an ID, and the size is 512 pixels by 512 pixels. You can change it to any size that you like. I like to stick with powers of 2 because those ones provide the best performance. Later on, I will explain the best performance on the GPUs when you want to parallelize programs. And then you would see that on the script section, we have a bunch of calls, at least one call to a library, which is Abubu.solver. And what it has is, I will explain one by one. There is a function that gets the source code for the fragment shader and the vertex shader that I explained earlier, and we will go through those source codes in detail. We have to access the canvas that we define, so we use the canvas ID to access it on the JavaScript side. So from the HTML page to get the canvas element that we want to draw on, we use the get element by ID, and then that returns the canvas for us. We define the geometry, which has a bunch of vertices, 0.5 and 0.5 and 0. This is the z coordinate, x coordinate of the next point, y coordinate of the next point, and z coordinate of the next point, and so on and so forth. Delete that one line from last line. Okay. 3 coordinates are necessary for drawing the triangle, and then the number of vertices for this triangle is 3. The number of coordinates for this shape that we are going to draw is a 3-dimensional shape. And the geometrical primitive that we are going to draw is a triangle strip. So the other options are lines, points, and triangle. And I will explain what is the difference between triangle and triangle strip if you're interested. The major difference between triangle and triangle strip is that when we want to generate geometries that are constructed of more than one triangle, then the difference between triangle and triangle strip become relevant. But here we work with the triangle strip. Then we want to construct a program, our WebGL program.
You have to give it a name. what happens if you don't give it a primitive name?
The default is the triangle strip. So any of these ones that is not provided, the default value would be
Will be a
taken.
triangle.
Yeah. So it will be a triangle strip if you don't provide any primitive there. But soon you will see that these ones are just for the sake of this tutorial, so you understand what's happening, what we are doing in the background. We won't be using any of these ones later on when we want to do calculations. We won't write any of these parts, but we will skip all of these parts. But the important part is here when we are defining a program, a WebGL program, basically. We are defining a solver. The solver has a vertex shader and a fragment shader. And the source code for those need to be provided in plain text. So either you can write down the entire source code in text, and you have to put it in these kind of things, like you could say precision, something, high precision, float. The entire thing would be inside this this single string, but we don't like to write in a single string of code. So to remedy that, we put the source code somewhere else. So this function is reading the source code with the ID of vertex shader from somewhere up top, but I will go through it. The fragment shader. The geometry that we want to draw is this object, my geometry, we are passing here. And the canvas that we want to draw on is this canvas 1 that we defined here. Now, all we need to do to run this program is we need to tell this program renderer that we have defined to be rendered. We call this render function of that, and it will use the vertex shader and the fragment shader to draw the program, to draw the triangle. Now let's look at the vertex shader and the fragment shader. So this is the vertex shader code that we are reading. You see it has an ID here, vshader, that we use down there to access the source code here. All the vertex shader codes and the fragment shader codes are written in GLSL language, GLSL. So the language of the shader parts are a little bit different from the JavaScript section. I will also put the what do you call a cheat sheet for the language. The reference is just like 3 pages long, so all the things that they can use. The language is quite primitive here. You determine what is the precision of your float variables and your integers. This high precision that we are using is basically single precision. The other options that you can have are medium precision and low precision. The other options are these ones: medium precision, low precision.
So what's the range of those ones?
So the medium precision is 16 bits and the low precision is just 8 bits.
And you will see a difference if you use them in speed, or really doesn't matter?
You'll see a difference in speed, but it will dramatically reduce the precision of the code, especially if you want to use them for doing computational work. For some computational work, medium precision and low precisions are enough. For example, if you're doing some sort of machine learning or deep learning, those kinds of things are lower precision values are fine. But if you are solving PDEs, I strongly advise against using those kinds of things.
Sure. Mm-hmm.
Then we have something, there are some keywords. The input to the program is a vector 4 type position. These are basically positions of the vertices that are coming in. And the program has a main part, just like a C program. And the main part has to be of type void. You have to define it as type void. You don't need to have a return statement, but you can also have it. It doesn't matter; it will automatically assume that you want to return. So the position, GL position. Remember that I said that from the physical world we use the vertex shader to map everything to the clip space. Here, our positions are basically inside the clip space, so we don't need to do anything with them. We just pass them as they are. But if you want to do any sort of matrix operations to do a transformation, this is where it's happening, where your position comes in, and then a final position is calculated. It's a vector 4 type. The first ones are X, Y, and Z. If the last value is 1, the geometry will be drawn on this screen. If the last value, I think, is 0, that coordinate would be ignored. This is used for rendering and shading really complex geometries. If you want to do complex transformations in computer graphics, that 4th dimension comes in handy. But we are not going to use it because we are going to just draw a 2-dimensional shape on the screen.
So values in between is not like transparency?
For the position part, no, it's not a transparency. It's something
So how
that is
do you
used.
use an integer like 0.5?
We can try it and see what happens. I haven't used it.
All right. All right.
The things that I use are basically these 3 ones. Even for the 3D simulations that I'm doing transformations, all of the transformations that I'm using is just using these 3. Usually the matrices that are operating on these ones, for rotation, I think you need a 4th coordinate, something like that. I don't remember exactly, but you can start manipulating these positions, but right now I'm not using any of those. Basically, this vertex shader is very simple. It gets the position, and it has it just passes the position as the position of the output position. So the output position and the input positions are the same. So this is a very simple part. The fragment part is, again, this is the fragment shader that is basically has an output, again, has the precision parts, has an output color of vector 4 type. It's RGBA values. The first one would be the red value. The next one is the green value, blue value, and alpha value. So here is where you can start playing with those transparencies. So when you're dealing with colors, then your argument of transparency becomes more relevant here. So it's a very, very simple program. If you run this one in your browser, it should draw this simple triangle for you. Everybody.
So is that vec4 thing? Is that a part of that GLSL language you were talking about?
Yes.
Does that just mean I am a vector with 4 elements?
Yes, correct. So the types that we have are float, are integer, put as a comment here, integer, float, boolean, vec2, vec3, vec4, matrix 2. These are rectangular matrices, matrix 3 and matrix 4. So these are in addition to these 3 basic C types: integer, float, boolean. you have vector 2, vector 3, vector 4, and matrix 2, matrix 3, and matrix 4, so that you can actually work with geometries. You can do transformations on the colors or the coordinates and stuff like that. So those are some basic matrix operations are provided through the GLSL language. Yes?
I think you said that the matrices were all rectangular, but I think that applies to all matrices. Do you mean they're all square?
Yes, square
Okay.
matrices.
Okay,
Sorry.
thanks.
I was drawing a blank on the technical word. Yeah, square matrices. All of the matrices are square matrices. Yeah, thank you. Okay, so this is just showing this a red color. You can change it in your program to become like green color. So if I change that one to 0, it becomes green, and the next one to, you can assume the next one would become blue. If you make all of them 0, what color do you think it will be? Anybody? Black.
Yeah, I'd assume black.
Yes.
Yeah.
Black, like my soul. Yeah.
I have a quick question.
Sure.
Is it always exactly one fragment shader that is used by a vertex shader, or can it like have multiple vertex shaders for different positions within it or something like that?
So basically, for the entire geometry that you pass through will go through the vertex shader first. All the vertices will be analyzed, and once they are analyzed, the program goes to coloring, and then that's the fragment shader. But does this mean that for the entire computations we should just use one fragment shader? The answer is no. We can have multiple different sections of the program that they are calculating different things. They can have different types of fragment shaders or vertex shaders for different purposes. As an example that I can give you is, for example, not this one. So this program basically has some parts that is calculating the geometries, a vertex shader that is rotating this object, and it's creating the final calculations. You can have a different fragment shader that is calculating everything for those purposes. So your overall program that you will use WebGL for will have multiple different sections. But each of those programs that you combine a vertex shader with a fragment shader, it can have only, each section can have only one vertex shader per fragment shader. Does that answer your question?
Yeah, I think so. So just to be clear, you're saying that each fragment shader corresponds to a single vertex shader?
Correct.
All right, yeah.
So Abusar, I was playing with the last element of the GL position. So it can be integer and or integer or a fraction, but it seems to be inversely proportional to the size. So it's like scaling. So you can scale by half if you multiply by 2, or if you, you can make it bigger by putting 0.5, or make it half the size by putting 2, or 1/4 by putting 4. Seems like scaling.
Ah, cool.
Yeah. So but it's an inverse scaling. The bigger the number, the smaller the figure.
Yeah. Yeah, it has something to do with the scaling. Okay. I don't use it. I don't mess with it.
We should not then.
Yeah.
Follow the teacher.
Yeah. So if I want to make this one a rectangle instead of a triangle, all I have to do now is add a vertex here and then basically I would have two triangles connected to each other. So in this line of the code that we had the vertices, I can start having sorry, you can see I can have code completion in Vim as well. Okay, and then I have to make sure that I'm saying that I have 4 vertices, otherwise the fourth one would be ignored. You see the two triangles are stitched together, and the way that now the triangle strips work is that the first 3 are used for the first triangle, and then subsequently and the next line is added, and these 3 ones are used by just moving one vertex down. The next 3 are used for drawing the next triangle here. Okay.
And is that this might be a stupid question, but I'm not familiar with this field of math. You can make any arbitrary polygon just by stitching together triangles like that?
Yes, correct.
And I don't know how much we'll be getting into like the 3D stuff, but do they also tessellate over any arbitrary 3D geometry like that?
Yes,
Okay.
yes, correct. So actually there are other parts like tessellators and stuff like that that actually are in charge of doing those parts, which you can technically program on your own in WebGL. But for computational purposes, we are not dealing with tessellators. Those are like advanced computer graphic parts that are related into dealing with complex geometries and stuff like that. They are used in complex geometries as well as when you are dealing with lighting. If you have a rough geometry, or if you have a complex geometry and you have different light sources and you want to calculate light bouncing off of these stuff, it becomes a complex problem that you can deal with. You can handle a lot of these ones in the vertex shader, fragment shader, tessellators, and stuff like that. So all of those ones can be implemented in general. But what I wanted to say here is that if we add a fourth one into the triangle strip, now these maybe a different color would be appropriate. Now these 3 would be used to generate the triangle strip. If you use the triangle version of the primitive, basically then after the first 3, you had to add another 3 vertices to generate the other triangle. So, and then you could have one triangle here, another triangle somewhere else. So they didn't have to be connected to each other if you were using triangles rather than triangles. So triangle strips are useful if your geometry is complex and you want to add a lot of points into that, so you can loop around them, and with the minimal number of transformation of data, you could generate the entire geometry. Triangles are useful if you have disconnect portions and you don't want to deal with ordering of the triangles and so on and so forth.
Now here,
So I have a question.
Before you, can you go back to your figure? Yeah.
Sure.
So if I think Max had a question. You can go first.
Yes.
Oh no, it was Geraldo.
Hi.
How? Yeah, hey. How do you troubleshoot code in here? Is there any sort of trace path for any errors that might happen? Does my file stop working completely and I am getting no feedback from the program?
Okay. So if you press F12 on this side and just press selected context only, so it doesn't throw miscellaneous errors for you. If I change something, for example, if I have a typo here in my fragment shader, I could just write a 1 here without anything. The fragment shader will not compile because there is a syntax error there. But what's happening here when I'm defining this solver is actually it gets the source code for the vertex shader and the fragment shader. It compiles these source codes in the background. So if there is a syntax error somewhere, the code cannot compile. And if it cannot compile, you won't be able to run it. But it tells you in what line the error is happening. Error 14, there is a syntax error. And if you look at it, there is this one here. So at line 14 of this one. So you can put a semicolon there and it will become happy, or you can remove that one. Also, I don't know, you can.
So it's sort of small on my screen. Are you just looking at the console of like the Chrome DevTools thing?
Yes, correct. If you press F12, let me see if I can. Okay, is it visible now?
Yeah, it was before. Back a little bit more.
Yep.
A little bit better.
Let me.
That's fine. That's a good size.
A good size now?
Yeah.
Okay. So if I introduced an error here, it should probably complain. Let me see. Yeah. So if there is a JavaScript part error, we are at the messy, that the canvas is not defined, and you can click on that. It says on line 86 of the code, you see this element canvas is not defined, and the reason is that the name of the variable is actually canvas_1. And if I fix that, the error will be fixed.
I found out my error was that I used a period instead of a comma when I was adjusting the vertices.
Okay.
So, yeah. All right, thank you.
So then you're welcome. So what I want to do next is basically
before you go to the next one,
yes.
here I just one question. So I don't know the view or how it works. I mean, because if I have changed a little bit the numbers, it's not exactly it's triangles still, but I don't understand. For example, in line 72, if you put instead of 0 at the end, the last point, put a 5, for example. No, yeah, put a 5.
Oh, this is the z coordinate. If you do
so
that, basically it will push it like that, and the geometry that is getting projected on the screen. Remember, let me
right.
share the.
But the thing is, I don't understand the projection. Yeah, because I get like an L. So I don't know. I don't know if follow the projection. So later on, there's a way to change the angle of the camera so we can see what is.
Oh, you can't. The camera, you have to design it yourself. There is no camera. So basically, this is the projection that is happening. So if you make that one, that shape gets distorted a little bit, and the lines that get projected on
if you put
the
a 5,
screen.
for example, it looks very strange. You put a 5, it looks like an L.
Oh, if you put a 5, basically, then you would go out of the clip space. You are going out of the clip space. So part of the triangle.
1.
Yeah,
I see, that's right.
Yeah.
All right, thanks.
Okay, you're welcome. Okay, so the next thing that I want to do is we can change all of these 0.5s to 1 so that we can have a unit rectangle rather than a 0.5 size. And I have a ulterior motive for defining the rectangle like this. Okay. Now if you can see that I change these geometries like so that I'm drawing that type of rectangle. I can now stop providing any sort of geometry to the solver. You see, I commented out all of these lines, and I've removed the line that was providing the geometry. I'm still drawing the same thing, so just to make sure that I'm not providing any geometry anymore, I removed all the geometry that was there. Okay. Still, I'm drawing the same geometry. And the reason is that I have a default geometry set up as a unit rectangle that we would be always drawing. The reason is that for all the computations that I'm going to do is that I'm going to assume that my domain is going from 0 and 0 from the bottom left corner to 1 and 1. And then you can easily map other stuff that you have. But you will see that there are other stuff that are important in that section as well. So if I wanted to now map this corner to be as it is, but I wanted this unit rectangle to cover the entire screen, all I have to do is I can play with this vertex shader a little bit. If I multiply the x position by 2 and subtract the 1 from it, then basically I'm going from, for the fragments, I'm going from -1 to 1, right? So if I'm doing that, then the x coordinate you see is mapping to that. You can do the same thing for the y coordinate. You can multiply it by 2 and subtract the 1. And it will do the same thing. You can do interesting stuff with the notation. You can see that I am multiplying both x and y by 2 and subtracting a y. I can use some of the notations of the GLSL language and do it as a vector operation. Now, if I do it like that, the xy coordinates would be a two-dimensional vector that is multiplied by 2, and element-wise I am subtracting a 1 from both of them. Still doing the same thing, right? Okay. So we are drawing a unit rectangle that is covering the entire canvas for us. Now, one other job that the vertex shader is really good at is interpolation between the vertex values. So it can actually, in addition to calculating the position of each of the vertices, it can also do some sort of interpolation based on the vertices over the fragments so that the fragment shader can use it. So in order to do that, the type that the keyword that you need to use is an out for the vertex shader. I want to calculate a vec2 type vector that is my pixel position. Remember, this will be an interpolated value, so this will be an interpolated value done by the vertex shader. And my pixel position would be interpolated using the xy positions of the vertices. Okay, so it seems that I'm saying that the pixel position is the xy position of the vertices, but what I'm actually doing is that as I'm making this an output, it will generate an interpolated value for between the x and y positions of the vertices. Now I can use that one inside the fragment shader, and the output of the fragment shader can be used as the input of the output of the vertex shader can be used as the input of the fragment shader by using the in keyword, rect2, pixel position. Now instead of the x value, I can the the red value, I can use the pixel position X. Now, in this corner, the position X of the vertex is 0. In the right-hand corner, the position of the vertex is 1, right? So the untransformed version that I'm using for interpolation. So anything in between would be interpolated from 0 to 1. If I do that, you see you will have a gradient of colors going from black all the way into red. You could do it with the y coordinate, and then you would go from here, 0, all the way to that point would be 1. You could do it in the green part. Green is gradually changing there. You could mix and match the two. Now the red value will increase in the y direction. The green value would increase in the x direction. And the combination is this color.
Could you add like two? Could you add pix position dot y plus pix position x as one entrance?
Can definitely do that. One part is that you need to, so this is, you can see that it's going diagonally, but if you want to make sure that you're not overflowing, when you are drawing colors, the colors should change between 0 and 1, and right now you are going between 0 and 2. You can multiply it by 0.5. And then you would have the effect that you were expecting.
Right.
Okay. If I don't provide any vertex shader, there is actually a default vertex shader that does these stuff for us. So if I didn't provide any vertex shader, the vertex shader that I have will be the one that has this output vector 2, and it has this one as well. I like to use this CC a lot for the center coordinate of the pixel. That is exactly the same as the previous one, position XY. So both of these guys, so this vertex shader is actually default everywhere. So if you remove this vertex shader completely, and if you don't provide any vertex shader to this program, the default vertex shader in the library is exactly what we had before. So for most of the remainder of what we are going to talk about, we will use that default vertex shader that we have over there, so you can have an additional vec to CC. And you can use either one of them that you prefer, so you can have like CCX here. Prefer that. So it has a default vertex shader that is working on this unit rectangle geometry, and it's multiplying the x and y coordinates by 2 and subtracting a 1 from them. So basically, everything is being shown there. From now on, we will be now concentrating on just the fragment shader, and I will have just one more example here based on these coordinates that we have. So one thing that I want you to notice is that we are coloring the entire rectangle, but there is no for loop anywhere that says loop over the pixels or anything like that. We just have a recipe for all the pixels, and the coloring is done automatically for all the pixels. And this render is basically doing and coloring the entire geometry. So this part is quite important to understand, that there won't be any looping over these ones, over the pixels that you have. The looping is done automatically. Now, you can have if conditions like so, that you can say the length of this CC minus a vector 2 of 0.5 and 0.5. This basically calculates the modulus of the vector. It gets a vector 2 or vector 3 or vector 4 type, and it calculates the modulus of the vector, this function length. And if we say it's less than 0.2, color it like so that we were doing, else the out color is a vector 4 type of 0, 0, and 0, and 1. Basically, what we are saying here is the length of this CC vector, the distance.
You need to close the parentheses.
Yes. By the way, blocks of code are marked with curly brackets. So we can have an if statement like that. If the distance from 0.5 and 0.5, which is the center of this rectangle, is less than 0.2 units, we will color based on what we had before. Otherwise, we would color it black. Okay, so that the philosophical question here is that what is the underlying geometry that is being colored right now? Is it a circle? Any answer?
Well, it depends on the scaling you have, right? You did 512 by 512. If you do 6 by 6, then it's going to look very very different.
No, but what is the underlying geometry that the
it's still a square. Still a square, but you're just only plotting.
It's still two triangles basically that we are coloring. So it's not really a circle that we are drawing. It's two triangles that they are colored such that they create this illusion of a circle. So and you can say that it's a square. If you make we can play with the resolution a little bit, but we need to do quite a lot of zooming so that you can see the effects. I don't know how much we can zoom, but you can see that there are two things that are basically two corners, or it's just a cross. Make it maybe 20. And now you can see that the pixelation and the fact that how the fragments are being generated. And being colored, that makes all the difference. I think I will stop here, and then we can pick up from where we left. You can start playing with these if conditions and generate a different geometry if you want. You can push around this circle. You can play around with the colors you have. You can play with the transparency value. The underlying color is white, not 5, but 0.5. So the transparency is between 0 and 1. Make it really transparent. It will look almost like white.
I think this would be pretty good.
Yeah. Can stop here because if I want to continue, it will become too long and you would lose your interest.
413. No, I think this was really good, first class, Abusar. Thanks so much.
Yeah, thank you. Can I ask the one thing that I sort of got lost in the flow while I was watching? What was the motivation between having CC and PixPause if they both have the same information in them, or did I miss something there?
So I was using pixel position as I started programming in WebGL, and this pixel position was the default vertex shader, and I always explicitly had the vertex shader there, and I was constantly using that same vertex shader over and over, so I created a default version, and then the pixel position was too long to write it, and then I had II for the for a unit vector in x direction and JJ for a unit vector in the y direction, and I noticed that it would be more logical if I want to shift compared to something, I would shift compared to the center. So CC was born somewhere down the line. So I had a bunch of legacy code that was still using pixel position, and I still left it be there. Also, some of the cardiac models, they have this. It is very likely that you would see one cardiac model that you are trying to convert that has CC as one of those variables that are born somewhere that is representing something. So you can't use both of them. So you had to switch back to pixel position, or you have to rename that variable. So both of them, they exist, and you can use them interchangeably.
Okay, but
yeah.
like in this example that you're doing right here, they're basically the exact same thing.
Exact same thing. So you can just use one of them.
Okay.
It doesn't matter. Yeah, you can just use CC for both of them.
Yeah, that's what I was confused about.
Yeah.
So thank you.
Yeah, you're welcome. Exactly does the same thing. Any other questions? No?
This might be getting ahead of things, but like, how much use can you get out of the dev console in your browser, or for like, can you like profile the performance of it and actually see what's going on, or like run shaders from the console, or is that not really possible?
So from the
Like,
console,
can I run an Abubu.solver?
yes, you can actually do that. For example, if you so there are other stuff that you can do that I didn't show here, but it's totally possible to do. Is that if you open the source code like so, you can start. This source code is showing the library. This one. You can start changing your stuff here directly. I think it was possible to edit the code if I remember correctly. Doesn't allow me right now to edit for some reason. But you can edit the source code here.
I think you're not sharing your screen right now.
Oh, sorry.
Yep.
So that the source code actually can be edited. Right now, I don't know why it has stopped allowing me to edit. But technically, you can start editing the code, and what you can see, you can do breakpoints and stuff different in the different sections of the code. In the console section, right now, what we have defined is that renderer. it exists there. You can render it. You can ask to be rendered again, and it will define that. If I had commented out this part, so the program wasn't actually rendering the screen, so then if I called that, it would actually render the program. So in the console, you can do a lot of these stuff. You can change variables. You can play with a lot of these stuff and recall them and see what happens. So it depends on how savvy you are and how much you want to change here rather than changing in your code. I personally change the code and refresh because that seems to be easier for me. But there are times that I'm actually changing variables here through here, or I'm displaying the stuff here. You can start dumping the values from the GPU here and print out values for debugging purposes. You can use a lot from here. Those error messages regarding this part that you saw here that I introduced an error somewhere is all from the library. So without the library, you wouldn't see any of these errors. So you were at the mercy of. I spent a lot of time to develop the debugger as well. So yeah, you can use it. That depends on what debugging experience you have. If you have all your life used an IDE, this is pretty rudimentary for you. If you're a text editor kind of guy, it has a lot of features that you can use. Okay, I stopped recording.
Yeah, no, I'm happy to see about the debugging. I didn't realize you added that yourself, but that's going to be super useful to have.
Yeah. One part that you will probably notice later on if you start programming is that debugging a parallel code is by nature difficult. So you can't really have a certain debugger that tells you exactly what's happening somewhere. So there are other features that I have developed that is just actually outputting the data that is over the GPU. You can monitor it. You can make the size smaller, like what we did for the circle here to make it smaller so that it becomes a more manageable size to see what's happening, what's going on, what's going wrong. But since everything is happening in parallel, you don't see many parallel tools that are for debugging parallel codes. So that's a general problem that exists. Suddenly 3,000 cores are launched to calculate something, and one of them, some error happens on it. It's not exactly like CPU that you can see exactly at what moment of time, what number caused the problem. So the problem exists there.
Speaking of that, another question I was wondering, is the size limited by the number of cores in your GPU, or will it just like start reusing cores if it needs to?
So if you read here, there is this website called WebGL report. WebGL report version 2 for WebGL 2. You will see that there are certain limitations for your GPU, and the maximum viewport dimension that you can have is this size. So if it's, you can see 16,000 pixels by 16,000 pixels on this GPU. But the number of cores that you have is certainly less than that. Because for this one, I think is around 3,000 cores of GPU. So they will be launched and they will be coloring part of the frame buffer, and then they will go to the next part and they will color that part, and they will move forward until all the image is colored.
Okay. Thanks.
You're welcome. Any other questions? If not, I will stop here.